I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science and engineering. My name is Andrew Falkowski, and I'm joined as always by my trusty co-host, Taylor Sparks, and our audio guru, Jared Duffy. What's going on, guys?
Dude, we had 10 puppies this week. My dog had 10 puppies. So I'm just asking for a friend, where exactly do you put dog midwife on your academic CV? Is that like an education? Where do I put that?
In the experience
that's
section.
life experience
Life
section.
experience, yeah, delivered.
Yeah, so that was wild. That was a good time. How about you guys? What's new? You survived finals week?
You know what? I'm reaching this point in finals and just in school in general where I'm really liking that we're at such like a high, quote unquote, academic level where teachers are like, I don't need to test you. Like, do a project. Yeah, I like that. I don't want to sit somewhere for 4 hours and do like 3 homework problems. That's the worst. Is you're like this too, Sparks. I'm looking at you. Is the teachers who are like, I'm going to give you so much time to do 2 questions, and these 2 questions are going to be a year long each.
Oh, yes, academic rigor. It's a dying art.
Yeah, I mean,
I still practice it.
You know.
One of my finals, the professor is like, okay, you have all day to do this, but it's going to be scaled appropriately. So it was 12 essay questions, and it took like 5 hours. It was awful.
Was that an engineering class?
Yeah.
My econ,
looking at metallurgy.
My econ teacher accidentally deleted the class the day after the final. I didn't know how to respond. I woke up and I was like, oh, when I did that final, I'm like, did I take econ this semester?
Gone.
And then, appeared a week later. He's like, oh, sorry, I clicked the wrong button, guys. I was like, you know what? Whatever, dude.
Well, today we have quite the episode. Andrew, what are we talking about?
We're doing a follow-up to a previous episode where we first did a deep dive on the science behind additive manufacturing, and now we're going to dive into a couple case studies of additive manufacturing or 3D printing, whatever you want to call it, and look into some interesting applications and the materials that are getting involved there. Now, we're really just scratching the surface, as always, with a lot of these topics.
There's so much you could cover here.
Yeah, we just chose a few really interesting case studies that I think show what's possible and things that are really interesting that are being done with 3D printing now.
Some of these we've already done episodes on, and some of them we haven't. And if you really would like an episode on that, be sure to hit us up on Instagram and let us know, and we can obviously churn out some new episodes related to this. We do have quite a long list of episodes planned, but we're always looking for new ones, so just let us know.
Yeah, the backlog is seemingly infinite.
Yeah, every time someone's like, oh, you should really do this, we're like, oh, well, we have that planned in 6 months, so don't you worry.
That doesn't mean you shouldn't ask, because the whole reason we're doing 3D printing is because people have spoken, and we delivered.
Always ask, because I definitely think there are times where we're like, wow, how did we miss such a simple topic? We got to do it.
Yeah, or we have something planned that's kind of lame, and then someone suggests something, it's like, okay, that's way better, we're going to do that.
Yeah, for sure. Let's dive right into it, Andrew. What's our first topic?
All right, first we're going to talk about 3D printing shape memory alloys. We did an episode a while back on these materials, essentially a material that can remember an original shape. So you can deform it and then apply either heat or unload it, and it'll return to that original shape. So there's 2 real mechanisms here. There's the shape memory effect, and that's where if we deform this material, we shift it to a different phase, and then by applying heat, it will return to its original shape. The other effect is known as superelasticity. So these are metals that can undergo up to 8% strain, and then upon unloading, recover back to their original shape.
That is so nuts.
The main material that's used in shape memory alloys is nickel titanium, or nitinol, and it has been a pretty big focus in the additive manufacturing world, trying to create and print complex shape memory alloys. Now, typically these were made with either casting or powder metallurgy, but these had a couple of problems, mainly because impurities are a big problem and they hinder the shape memory or superelasticity effects. So casting ends up resulting in the inclusion of a lot of carbon and oxygen impurities, and these will result in titanium-rich phases that dampen performance. Additionally, casting requires machining, and nickel titanium is a pretty ductile material, so it's actually pretty difficult to machine.
Oh, that's funny. I usually think of it the other way. Like really hard materials will ruin your bits and stuff, but when it's ductile, it makes it hard to machine as well.
Right, it's a lot tougher, and things might tend to stick around. You might have...
They'll sort of bend instead of chipping off or whatever.
Right, yeah, I think that's what's going to happen here.
Interesting.
Additionally, if we try to use powder metallurgy, it addresses a lot of the machining issues. You can get better surface finishes and more complex parts, but the surface area of the particles that are being used prior to sintering causes them to be much more reactive with oxygen or carbon that's in the crucible, and so impurities are still a big issue. And additionally, even though you can resolve some of these impurity issues, part complexity is still a big issue. You're not going to be able to create anything particularly complex or intricate via these methods. So this is where additive manufacturing comes in, right? We're able to create on the spot pretty complex shapes by bonding these powders together. And so we're able to make up for a lot of these defects. Additionally, these are typically done under inert atmospheres anyways. So we solve a lot of these impurity issues. There's no carbon crucibles. You typically don't have any oxygen in the chamber when it's being made as well. So you can overcome a lot of those impurity issues. Before even getting to the fabrication standpoint, it really starts with the powders themselves, because that's what's going to end up forming our melt and then solidifying. So if your powders are the wrong composition or they're not alloyed properly, you're going to run into issues. You also need these powders to be pure already, right? We need to have, I think there's the standard, if they're going to be used, especially in a biomedical application, it has to have less than 500 parts per million impurities. And so in order to achieve a nice pure material, they actually end up using electrode inert gas atomization. And so unlike maybe a typical gas atomization approach where it's heated up in a crucible and then a gas is used to spray and create droplets, in this case they use induction coils such that the initial ingot is actually suspended in air and doesn't make contact with the heating elements, so it's magnetically suspended as it heats up and melts. And then using a high pressure gas, they're able to separate into small droplets, which can then be collected. So these are nice and spherical. They haven't contacted any crucibles, and so they're also pretty
all before
pure.
You've ever done any of your sintering, all of this work goes into the precursor preparation.
That's right.
And
yeah.
welcome to powder metallurgy.
And they also, they want to have these powders to be very fine and very uniform as well. In our previous episode, we discussed how if your powders don't flow well, or they're too small or too big, you can have a number of issues with sintering. And so there's a lot of control that goes into this. Additionally, there's a point of selecting whether you're going to have a titanium-rich alloy or a nickel-rich alloy. Titanium-rich material demonstrates better shape memory effect and higher transformation temperatures, while nickel-rich materials demonstrate superelasticity after some processing.
Oh, that's cool.
Once we get to the actual synthesis part, the parameters that go into what's known as energy density come into play. If you remember from our previous episode, we were talking about selective laser sintering. Energy density is defined by the laser power divided by the scanning velocity, the hatch spacing, and the layer thickness. These are all parameters that you can vary during the synthesis portion to achieve different results. And when it comes to creating these shape memory alloys, they have a big impact. So higher laser power tends to increase the transformation temperature of the material, mainly because nickel gets evaporated because you're at a much higher temperature, which leads to a more titanium-rich material. Thus, you have a more dominant shape memory effect, and you have a more titanium-rich material, and so you have elevated transformation temperatures. So not only does this mean you can kind of control what the composition is, but it means you can also control, to some extent, the transformation temperature. We'll get to this in a little bit of why that's important. If you have a nickel-rich starting material, the same effect ends up being observed, interestingly enough. Even though you have more nickel from the outset, nickel ends up being evaporated in the same way. In addition, you have a lot of nickel-rich precipitates that ends up getting formed, and so these separate from the nitinol matrix. And so really you still tend to end up with a higher transformation temperature and the shape memory effect being dominant.
I wonder what role these precipitates play. Do they dominate, or is the matrix really still dominating properties in these precipitates? Or are they really strengthening it or something and changing its ability to deform?
They tend to pin dislocations, so they end up dampening the effect because they will create irreversible strain.
Gotcha.
So they're generally undesirable to form.
Gotcha.
What is interesting to note is, and this it probably is because a lack of impurities in terms of oxygen and carbon, nitinol that's made from this additive manufacturing approach tends to have less irreversible strains compared to conventional hot worked nickel titanium. Additionally, they tend to have a higher micro hardness, and this is due to the buildup of residual stresses in our material. And but these are again dependent on our scanning velocity. Additive manufacturing approaches also improve the mechanical properties of nitinol, so this tends to increase the fracture stress, and differences in energy density that are being applied can almost double the failure stress of these materials, and they can almost increase the failure strains by 10%. So you get a pretty wide range of properties depending on your energy density that's being used. And what's really cool about this is now, because we can adjust these parameters on the fly, right, it's being computer controlled and controlled by a mirror, different locations of the part can now have different processing parameters and thus can have different transformation temperatures or different, strengths or hardness depending on what you want. So now in a single material, you can
totally
have
new functionality.
Yeah, you can have distance dependent properties built into that. I think one of the really interesting applications I saw was that somebody made a hand, and then different fingers of the hand were processed a little bit differently. So then
it
they
would like curl to actually like make a fist or something, where some have to deform more than others or something.
Well, they put it in boiling water, and as they raise the temperature, slowly one finger at a time tends to close.
Dude,
which
that is too cool.
That's kind of a silly example, but thinking about this in a maybe an aerospace application
It's just
or
another
in an
degree of
automotive,
freedom, man.
you have a lot more control, and this means that instead of having to have several actuators that are dependent on maybe a time reaction or need to come in consecutive order, you can now bake this into a single material and get that same response.
That's rad. Very cool.
What's also really great is that we talked about manipulating the phases that are going to be present with different laser power, but because they can adjust where the lasers are, how the hatch spacing and the distance, they can also engineer porosity into these materials. So nitinol, because of that super elastic effect, is really a promising material in prosthetics because the super elasticity is actually really similar to how bone deforms and acts as well. And by engineering porosity into these materials, they're not only biocompatible, which is pretty rare and amazing themselves.
Regrowth now. Yeah.
But it can form a great lattice for bone regrowth while still
that's
maintaining something that can deform in a way that the body expects it and is healthy. So there's a lot of work into creating really custom geometries to meet the needs of specific, implant requirements and tailoring these responses to get that.
So it's not just manufacturing cool new shapes with additive. This is cool new functionality. That's rad. I like it.
And it's not just nickel titanium. There's other metals out there that have been demonstrated to be 3D printable and demonstrate this shape memory effect. In fact, there's a growing field, and the term that's been used to kind of describe it is 4D printing, which I think is kind of a silly buzzwordy name. But the idea here is right now, not only are we adjusting and printing the geometry, but we're printing responses as well. And there's a time component to it in addition to that. So
pretty cool.
If we look at stereolithography, we can make polymers. They now have these printers where you can make your own custom formulated resins. So they can print these shape memory polymers as well and create all sorts of interesting, complex shapes that have different responses to stimuli.
Man, that's rad. Well, very cool, man. Our second case study, you started out talking about, shape memory alloys that can be used as actuators. Our second one is also having to do with actuators. So switches, basically, like things that you do something and it does some sort of response, mechanical or otherwise, typically mechanical. This has to do with what are called interdigitated dielectric elastomeric actuators. Quite a mouthful. This comes from my former PhD advisor, Dr. David Clark, and his collaborator, Jennifer Lewis, both of them at Harvard in the School of Engineering and Applied Sciences. And it's pretty cool. So he, when I moved with him to Harvard back for grad school, he started going down this rabbit hole of working on elastomers, right? And at the time I was like, well, who cares about elastomers? And now it's such a cool field. So the idea behind elastomers, these are like rubber bands, right? These are squishy, soft materials. And you can do some cool things with them. So for example, you can make switches out of them. Now, there's lots of ways that people can make soft actuators. And this is important for robotics, right? Our bodies are basically made of soft actuators. Muscles are soft materials, but they can actuate, right? You can get them to contract or not contract and do different things to get muscle responses. So people that are interested in soft robotic materials are really looking after, soft actuators. And right now you could do like hydraulic, right? You could flow hydraulic, fluid into a channel and get it to change. That would be one way. You can rely on phase change. But what they are doing there is using electrostatic response. So the idea is, think back to our very last episode when we talked about supercapacitors. Picture that parallel plate capacitor from your intro to MSc class. You've got charges on either side of the plate. You've got some sort of dielectric material in the middle. Well, what do you learn about in basic physics class is that these different charges actually attract to one another. So they're going to actually be pulling closer in if you apply a large enough field to put a lot of charge. And if you have a material that's compliant, soft, it's actually going to squish down and it's going to bulge out the sides. So that's the principle behind it. And so it's typically kind of large voltages that they were working with. It's not like a 1 or 2 volts. They're typically a fair bit higher than that, to the point where you're worried about dielectric breakdown, right? If you get too high, then it will just, a little lightning bolt goes right through your dielectric material, burns it, and it's ruined. But that's kind of the idea behind these dielectric elastomers. So this is a field that's been studied a lot now. Some really cool things happening there. But the question is this, while they have some great things going for them, for one thing, they're fast, they're efficient, it's clear to me how they expand, right? You squeeze this plate so it's going to bulge out the outsides. How would you make it contract, Andrew? Any idea?
Could you just reverse the direction of the electric current so now you have a repulsion?
Yeah, that would be one way, is to basically have it be in the on state all the time, and then you take some voltage away, and that would cause it to relax. That's one way. Another thing they'll do is what are called pre-strained dielectric elastomers. And these, it's easier if you see a picture of it. It's sort of like a diamond shape, and they have rigid rods, and then you can change the voltage on which rods the current is across, and it switches from a sort of a vertical rhombus to a horizontal rhombus. So it contracts, but it's a trick in that it only is like anisotropic contraction.
Okay, so it's really it's expanding one way and then it's expanding the other way.
That's really it. So I mean, it kind of works, but people have pointed out that this is not ideal. Some of the problems is that, first off, the contractile strains are really a small portion of the total device area. They also point out that because they have these rigid frames, it limits the geometries that can be used. They have bad cycling and breakdown behavior, so they're not ideal. There has been another approach, though. You can take these vertically oriented electrodes, right? So you build up electrodes, and now you're applying the current vertically, so that they all squeeze together, which makes the overall device shrink, right? So that's the idea behind it. Picture like sheets of paper that aren't quite touching, and then you alternately charge positive and negative. So overall, all the sheets are going to kind of come together, so it's contracting, right? In that direction of the book, if you will, of the sheets of paper that are in. So that's why this title, interdigitated. If you take your figures and your fingers don't touch one another, but they go in between, you're going to oppositely charge these. And then when you apply the voltage, they're going to sort of squeeze together a little bit. I'm doing this, but no one can see it. But you can get the idea. And if you can't, check out the paper. The links are in the show notes. But here's what's cool. People have done that before using photolithography. Not surprising. The pain in the butt thing with photolithography is, let's say you want to do it for a different device or change the scale or anything else, you need an entirely new mask, and then you have to go through all the challenges which are inherent in photolithography process. You have to mask, you have to dissolve it away, you have to build it up, all this, etch it away, whatever it is. How much cooler would it be if you could just directly 3D print this? And that's what they did. So this was published in Advanced Functional Materials just last year. They used direct ink writing, which is an extrusion-based technique, so similar to the fused deposition technique we talked about in our previous episode. So they make their structures. What they use to actually print with is a polymer called PEG-PES, which stands for polyethylene glycol mixed with polyethylene sulfide. Now, the sulfide group's important because that's how they get it to polymerize, basically. There's a thiol reaction that they can do there. But in any case, it's a dielectric material. And then to make it conductive for the electrodes, because this is the electrodes that they're printing, sort of the fingers, they add carbon black. And there's lots of things you could add. Carbon black has some advantages. It's low density, it's low cost, it's actually pretty darn stable, and it can do something called self-clearing, which we'll talk about in a moment. So they add about 18%. It is enough to get it to percolate. It's now conductive, that's 18 weight percent. And now they've got their electrodes printed. So then this is what's cool. They then take these electrodes, which aren't touching yet by design, they're not supposed to touch, and then they turn it upside down and they cast it, the space in between, with a matrix, which is also a dielectric material. For this, they use polyurethane diacrylate. So this is a polymer, right? It's a type of, basically dielectric material. But they add a little bit of a plasticizer called dioctyl phthalate. I'm not familiar with the details of this. Now, in one case, you could add this plasticizer because it improves its mechanical, dielectric, and rheological properties. But I found that something that's really cool that they do with it is that it's also functional, in that if you get dielectric breakdown, destroying this matrix material, this DOP molecule can flow into those gaps and heal it afterwards, which is pretty rad. Anyways, one of the big benefits of this approach is that they get 9% strain. They're getting this huge improvement in cycling performance. They're getting really awesome breakdown strength. And it's just a really cool application of where 3D printing is not just some novel way to make a cool shape. It's actually giving you better performance overall.
Yeah, as we'll come to see, achieving those really fine structures is difficult with a lot of conventional manufacturing approaches. It just, the time commitment ends up being a lot more difficult. So when it comes to these really fine and intricate parts, that's where I think 3D printing really excels.
Okay, what's our next one, man?
The next one I'm going to cover is 3D printing in the aerospace industry. Now, this is also a pretty large topic, but I want to cover, maybe start with why the aerospace industry would be interested in these in the first place, right? These are supposed to be high-performing materials, high-performing engineering applications. 3D printing, isn't that just a bunch of welds? Why would they really be interested in these parts? Don't they need something that's, the best of the best?
Yeah, strength isn't typically its strong point.
And so this really comes down to reductions in cost and waste material. So if we compare additive manufacturing to the subtractive manufacturing process, so that's like a CNC machine, just removing materials to get the shape you want, there ends up being a 40% reduction in the waste material in metal applications in 3D printing. Additionally, about 95 to 98% of the waste material in 3D printing can be recycled. That is with the powder bed approach, which also means that you're equally reducing the amount of waste. Interestingly enough, a study by Airbus Group Innovations in UK, they showed that up to 75% of the raw material usage can be reduced by using additive manufacturing, as well as cutting their amount of CO2 that's produced through the manufacturing as well. Some studies have indicated that additive manufacturing has 70% less environmental impact than conventional machining. Interestingly enough, right, in aerospace, they're all about reducing weight without compromising performance. And additive manufacturing, because you have more control over the porosity of the part, and this porosity can be engineered, they're able to quickly actually reduce the amount of weight that the part has, and without necessarily compromising the performance.
Wow,
and so with that,
cool.
they can also reduce the cost, the fuel costs of different parts.
Now, is that just because they can leave like empty spots, right, where you don't necessarily have to have it solid all the way through? If they can, it doesn't require it for strength, and yet, so overall, they can put strength where they need it, but have the reduced density where they want it.
Yeah, exactly. It's kind of like an I-beam, right? They're able to remove all of that excess material because it's not necessary there.
Yep.
And in some cases, you need to have a certain shape, but strength isn't necessary in all the parts, and so they can engineer,
And our
more
bones
density.
do that, right? We have different. If people aren't familiar, your bones vary, right? They're really strong in some parts and much more porous in others, where the load's not as prevalent.
Yeah, and this isn't even just a projection either. General Electric specifically was able to reduce up to 25% of the production time and cost without compromising performance by shifting some components over to additive manufacturing approaches.
So cool.
But it's not all great. One of the major barriers remains structural performance. So they typically have a number of 3D printed parts have a lot of solidification defects, unwanted porosities or shrinkage cavities. You have oxidation issues in some cases, and they also tend to have anisotropic performance. So the property only works in one direction, or it's different depending on the direction that it's being sampled. But the industry has attempted to remedy these by including different fiber contents. So whether that's carbon fibers or fibers of other metal materials, they found that even by adding 1 weight percent fiber to the matrix powder, they were able to increase the flexural strength in some metals by up to 180%. In some cases, increasing the fiber content to now 1.5 weight percent, your flexural strength can increase by more than 400%.
Now, are these selective laser
Yes.
sintering? So they've just got these random particles of glass fiber or ceramic fiber or whatever it is, and it just doesn't melt. It just gets sort of included into it as the stuff melts around it?
Yeah, it becomes a composite. And I didn't dive too deeply into why this helps remedy a number of these issues. But from my understanding, it tends to be that it helps reduce the amount of unnecessary pores or cavities that form during it.
That's cool.
I think mainly by just providing a substrate that can be wetted and reducing some of that, as well as like shrinkage and residual stress issues. EOS is a particular leader in direct metal laser sintering, so SLS. They worked with Airbus, and they found that replacing the cast steel hinge bracket on Airbus A320 with an additive manufacturing titanium part, they were able to optimize, like we were talking about, where they were placing the metal and where the loads were, and they were able to cut raw material consumption for that part by about 75% and save about 10 kilograms per ship set on the planes.
Man, it's so cool seeing just case after case where you're seeing these big advantages.
Yeah, I think people talk about it. There's a lot of great articles, even in journals, that are like, oh, this is going to revolutionize it. Even like I was reading one from 2019 that's talking about how it's going to revolutionize it without providing case studies. And so it was really great to find a number of them.
Yeah, I've always thought that it's still academic. It's not really translating. So it's cool to see these translations to industry.
Yeah, and I think it really has to be like aerospace has enough money and they have such a demand for high performance that I think that they really are pushing it and showing these great applications. This next one,
and weight is such a big deal for them. So additive is a great way to shave off weight.
Oh, for sure. So this next application, so NASA wants to develop new technology for Mars exploration, right? So they were one of the first to fully 3D print a copper rocket engine sort of jacket. So essentially this is the cooling mechanism for the rocket nozzle. And I can't really show a picture because it's a podcast, but this is a pretty intricate, little part that they've got here. So it's essentially a conical copper shape that's pretty large. It took about 18 hours to make this, which is still quite a bit faster than trying to cast it and then do all the machining to it.
Out, yeah.
Yeah, but if you look at this thing, it has all these very tiny, well-controlled channels that are running through it. And the idea is they're going to run liquid hydrogen through this to cool it. But I took a metallurgy class that talks a lot about casting this semester, and trying to cast a part like this would be impossible.
Yeah, even fugitive wax, even with like the sophisticated ways to cast, would be such a nightmare.
These channels are way too intricate, and even if you could cast it, then trying to fix some of the issues that might come up with sanding or machining, it would be a nightmare. So
this is cool,
but it was also pretty difficult, right? They have over 200 of these intricate channels that I was talking about in the inner and the outer lining walls. Some of them were closed, so there wouldn't be any way to actually look inside or get access to them from external sources.
Which means when you put this together, the old-fashioned technique, it'd be a bunch of separate parts, which then you have to attach, weld, braze, or something.
That's
right.
But
here, this is one continuous piece you can make.
Yeah, exactly. And so they actually had to develop their own special copper alloy. And the reason for this is that copper is really good at conducting heat, but when you're doing selective laser sintering, right? Yeah,
that leads to part creep, right?
You want to keep your heat very controlled. You don't want your melt pools to extend so much, and so a lot of work went into engineering an alloy that would be sufficient and consistent for printing something like this. So it's not just optimizing these processing parameters. There's still a lot of work that's going into designing materials that can be successfully printed. NASA's not the only one 3D printing rockets. SpaceX has also successfully tested 3D printed engines. They have one called their Super Draco, and they've been able to put about 16,000 pounds of thrust through it as well. And this isn't made of any sort of trivial material either. They're using Inconel in these cases, which trying to machine Inconel is quite difficult. It work hardens, so as you machine it, it gets harder and harder. It ends up being quite difficult. So being able to 3D print it and avoid some of these machining steps is a huge benefit from a cost perspective, as well as reducing the amount of waste material that's coming out. And so they're actually still in the process. It may have already gone through. I think the article was a little old, but certifying this 3D printed rocket for human flight as well. Rolls-Royce as well has been able to create some pretty impressive 3D printed parts. Kind of like what we talked about, a lot of these parts that they're now switching to 3D printing are these really intricate geometries that would be just really a pain to try to cast and would be too difficult to machine and are too fragile in some cases to try to machine. One last thing that's more, I guess, on the space side. There's a huge interest in using additive manufacturing in space travel, right? For everything that you bring with you in space, right, that has a pretty big cost. And if you bring something that's unnecessary, that's potentially millions of dollars to bring that. And so trying to bring potentially additive manufacturing machines to Mars or to the moon ends up being a possible way. But you still have to bring material, right? Well, interestingly enough, some researchers at the School of Mechanical and Materials Engineering at Washington State figured out a way to 3D print parts using raw lunar regolith stimulant.
What on earth is that?
It's essentially moon rocks.
Oh, that is cool. So wait, they powderize it and then what? Fuse deposition? How do they do it? How do they bond it?
They use sulfur, actually. I'm not sure. I didn't look too deeply. We'll probably do an episode on it because there's actually a lot of literature
Sounds
on
like
it.
a cool micro episode.
But the idea here is that they, rather than having to bring bricks and other sort of construction things,
that is your starting material.
Yeah, they can mine the lunar rock there and use that as their material to build things.
Way cool. All right, well, our last one that we're going to talk about, Andrew acts like he's got these complicated channels in these engines. Tell you what's even more complicated than that, Andrew.
What?
Organs in your body. Man, these are filled with complicated channels, right? If you guys remember back a few episodes ago, we did one on bioprinting. You remember that when they print these things, there was this sort of gel scaffolding, and it was still hard, and those typically don't have these good channels in them. So this article comes from 2015 in the journal Biomaterials, and I loved it. They were able to do what's called coaxial 3D printing for embedded microchannels. Now, if you're familiar with coaxial cables, you know that it's a cable inside of another cable, right? It shields it. So that's the idea behind it. Instead of just printing one regular filament of all the same material, imagine now that as you print it using, say, fused powder deposition or something, fused deposition technique, imagine that it was a sort of core shell, that there's something on the middle that's different than the outsides.
Oh, interesting.
So, and then here's what they did. So, Andrew, have you ever seen these edible water bottles?
No.
You ever seen these? So we will do this on Instagram. Stay tuned. Another reason to follow us on Instagram is we do some cool demos. But you can make these edible water bottles that are basically like a gel blob, and the inside is filled with regular water.
Is it like that Japanese dessert? Or is that a
Yes.
is that a different
like
thing?
boba tea. I don't know if it's the exact same thing. It's similar. They might
not
be
like
the same.
boba tea. Isn't there's some sort of Japanese dessert that's like a bubble?
This is probably the same thing. So it's made out of seaweed. Well, it's alginate, which is derived from seaweed. And then, so you typically start with sodium alginate and calcium lactate. Now, the sodium alginate is your polymer. It's this long sort of regular polymer. And then the calcium lactate is just a salt. And what you want from that is just the calcium ion, right? So it's going to dissolve and just give you the calcium. And what happens is when you get these calcium ions near these polymer chains, they stick to certain parts of it and cause the chains from being like, imagine like they're long strands like of rope. But in the presence of calcium, they sort of take like a boat conformation. They kink, and then they form a gel, right? So those sort of hold them together. So basically, if there's no calcium, it doesn't form a gel. But if there is calcium, it will form a gel. So here's what they did that I think is so clever. If you look at the extrusion tip on this, they have the calcium chloride is what they're using for their source of calcium. It flows through the middle of what gets extruded, and along the shell around it is where the alginate flows. So then the calcium chloride, that calcium is going to diffuse into the alginate along the outside, and it's going to form a gel tube. So it's going to be hollow in the center because the center only had calcium chloride flowing through it. That's just a solution. But at the boundary between the center and the shell, that's where this now gel forms. So what you're casting is like veins, like in your body, are basically like soft materials that can print it wherever you want, and they're hollow on the inside. So this lays the groundwork for making all sorts of actual organs, right, out of biocompatible materials, gels and whatnot.
Or even think about microfluidics.
Yeah, absolutely. And you could obviously, just like we did in our previous 3D printing episode, you could embed cells into this if you want to, right? This is just showing the sort of the case study here. There's some cool figures in the paper they show when you introduce, say, dyes. They can see that it travels along these microchannels in really complex sort of organ type shapes. So I think it's really cool. It's a relatively simple reaction that, it's been around for a while. People making these silly sort of edible water bottle blobs for a while. But here they've made it high tech by introducing it with 3D printing to get this sort of coaxial solution. I thought that was pretty rad. And I thought it was cool that they pointed to the fact that other people had tried to do this before by taking just fluidic channels, basically where they'd put like if you've seen extrusion before, sometimes at the tip of the extrusion head, you could put a metal rod and it will force the material to go around it. So they were able to make hollow channels like that before, but it was complicated. You had to remove the templates afterwards. It could really only make like straight lines with uniform size morphology, which is not what your body does, because your veins get large, they go small, they branch, they change direction, and that just couldn't happen with the traditional extrusion. So then other people realized that, when you do electrospinning, which is a good future episode as well, electrospinning and with immiscible solutions, they were able to make coaxial extrusions. So what these researchers did is just put those two concepts together. They said, let's take these immiscible liquids, let's take this coaxial tip, and next thing you know, we can print hollow tubes of biocompatible materials. Pretty rad.
Yeah, that seems to characterize a lot of the recent developments in additive manufacturing. It's taking a lot of our existing technologies or ideas and now implementing that and combining it with the power of additive manufacturing to realize new possibilities.
Yep. Well, that's what we've got for you today. We are so glad you joined us. If you like the episode, do us a favor and check out our sponsors. We have some rad people that make this show possible. MatMatch, for example. If you haven't used MatMatch, check them out. matmatch.com. You've heard us talk about it before. It's all about helping you pick materials, and not just pick materials, but pick the people who will provide those materials to you. So if you're out there trying to buy Inconel or copper or whatever it may be, take a look, Google it on there. They've got some great guides and tutorials for different classes of materials. We think that you'll like them a lot. Their platform is used by lots of people every year. It's really easy and nicely put together. It's nice to see a company that cares about user interactions there. So check out matmatch.com. We think that you'll like it.
The Materialism podcast is also sponsored by Materials Today. You can visit materialstoday.com to stay up to date on the latest happenings in the material science field and read some of their fantastic articles that they've published. For this episode, we referenced an article from Farber et al., which will be in the show notes that you can check out. I thought it was really great. It did a good job covering shape memory alloys and reviewing how they've been used in additive manufacturing. You can also head over to elsevier.com to find more about their journals, books, conferences, and related programs.
And then the last thing, we'd love you to support the other people that make the show possible. For example, the people that make the awesome music for us. And now is the time for me to remind you that if you haven't left us an iTunes review, that will help us continue the grind as we climb higher. We're looking for that #1 spot in the chemistry category. We're in the top 5 right now. That's pretty fantastic, but we can keep climbing. So help us out. And obviously, connect with us on social media. We are regular users on our Instagram account. We would love to hear your ideas, to get feedback from you. That's actually where we get some of the best ideas for our shows, is from listeners that come up with great ideas. And we are also posting cool videos, answering questions, and generally sharing the random ideas that pop into our head on that site. So check it out.
Catch you next time.
Have a good one, guys.
See you next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.